Neutrons play a silent but decisive role in controlling atomic stability and behavior, and understanding this single idea reveals why matter itself can exist in a structured, lasting form. At first glance, neutrons seem almost unimportant because they carry no electric charge. In a world where physics often highlights attraction and repulsion between positive and negative charges, a neutral particle may appear passive. Yet this neutrality is exactly what allows neutrons to perform one of the most critical functions in nature: maintaining balance inside the atomic nucleus. To understand this, we must look inside the atom. At the center of every atom lies the nucleus, a dense core made up of protons and neutrons. Protons are positively charged, and according to the laws of electromagnetism, like charges repel each other. This means that inside the nucleus, protons are constantly pushing away from one another with tremendous force. If this were the only force at work, atomic nuclei would instantly break apart, and stable matter would be impossible. The universe would be a chaotic cloud of subatomic particles rather than a place filled with stars, planets, and life. Neutrons solve this problem through their involvement in the strong nuclear force. This force is one of the four fundamental forces of nature and is incredibly powerful at very short distances, such as those found inside a nucleus. Neutrons contribute to this force without adding any electrical repulsion. Because they have no charge, they do not increase the electromagnetic push that already exists between protons. Instead, they add attractive strength, acting as stabilizers that bind the nucleus together. In simple terms, neutrons function like buffers, reducing internal conflict while increasing unity within the atomic core. The importance of this role becomes clearer when we compare different atoms. The simplest atom, hydrogen, has only one proton and usually no neutron. It can exist without neutrons because there is no proton repulsion to overcome. However, as soon as an atom has more than one proton, neutrons become essential. Helium, for example, has two protons. Without neutrons, those protons would repel each other too strongly to stay together. The presence of neutrons allows helium to exist as a stable element, and the same principle applies to all heavier elements. Neutrons also control atomic behavior through their influence on isotopes. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. While the chemical behavior of an element is mostly determined by its electrons, the physical stability of its nucleus is strongly affected by the neutron-to-proton ratio. If there are too few neutrons, the nucleus may be unstable because proton repulsion is not adequately balanced. If there are too many neutrons, instability can also arise due to internal nuclear stress. This delicate balance shows that neutrons are not merely fillers. They are regulators that determine whether an atom will remain stable or decay over time. This decay process, known as radioactivity, further highlights the decisive role of neutrons. When an unstable nucleus decays, it often does so because its neutron configuration is unbalanced. Some nuclei emit particles or energy to reach a more stable state. These neutron-driven processes are not just abstract concepts, they have real-world consequences. Nuclear power plants rely on controlled neutron reactions to produce energy. Medical technologies use radioactive isotopes for imaging and cancer treatment. In all these cases, the behavior of neutrons determines whether energy is released slowly and safely or rapidly and destructively. Beyond individual atoms, neutrons influence the large-scale structure of the universe. In stars, nuclear fusion depends on precise nuclear stability. Neutrons allow atomic nuclei to combine and form heavier elements, releasing energy that makes stars shine. During extreme cosmic events such as supernova, massive numbers of neutrons interact with atomic nuclei, leading to the creation of heavy elements like gold, silver, and uranium. Her beauty. What makes the neutron's role especially remarkable is its quiet nature. Protons define the identity of an element, and electrons determine how atoms interact chemically, but neutrons operate behind the scenes. They do not attract attention through charge or visible effects, yet without them, atomic structure would collapse. This teaches an important scientific lesson. Influence does not always come from what is most obvious. Sometimes, the most critical components are those that work silently to maintain balance. In conclusion, the keynote that neutrons play a silent but decisive role in controlling atomic stability and behavior captures a fundamental truth about matter. Neutrons stabilize nuclei, regulate atomic balance, enable the existence of elements, and power both cosmic and human-made processes. Their neutrality is not a weakness but a strength that allows them to hold the atomic world together. Without neutrons, there would be no complex atoms, no stars, no technology, and no life. Through their unseen influence, neutrons prove that even the quietest particles can rule the structure of the universe. Without neutrons, the structure of matter and the universe as we know it would not exist. And this idea reaches far beyond atomic theory into the very foundation of reality. Neutrons are not just supporting particles inside atoms. They are essential architects of existence. Their presence determines whether matter can form stable structures, whether elements can grow beyond the simplest forms, and whether the universe can evolve into something complex rather than remain a formless sea of energy and particles. To understand why the universe depends so deeply on neutrons, imagine a reality without them. In such a universe, atomic nuclei would consist only of protons. Protons carry a positive electric charge, and identical charges repel each other strongly. Even a nucleus with just 2 protons would experience intense internal repulsion. Without neutrons to counterbalance this force, nuclei would be unable to stay together. This means that only the simplest atom, hydrogen with a single proton, could exist in any stable form. All heavier elements, from helium to carbon to iron, would be impossible. This limitation would immediately strip the universe of complexity. Chemistry, as we know it, depends on a wide variety of elements. Carbon forms the backbone of life. Oxygen enables respiration and combustion. Iron builds planets and fuels stars. None of these elements could exist without neutrons stabilizing their nuclei. A neutron-less universe would be chemically barren, incapable of forming molecules, minerals, oceans, or living cells. It would be simple, empty, and lifeless. Neutrons also make the formation of stars and galaxies possible. In the early universe, after the Big Bang, matter began cooling and forming the first atomic nuclei in a process known as nucleosynthesis. Neutrons played a critical role during this phase by allowing protons to combine into heavier nuclei. Helium, the second most abundant element in the universe, requires neutrons for its stability. The formation of helium allowed matter to clump together under gravity, eventually leading to stars and galaxies. Without neutrons, this chain of cosmic construction would have stopped almost immediately. Inside stars, neutrons continue to shape the universe. Stellar fusion depends on the ability of atomic nuclei to merge and form heavier elements. Neutrons help absorb excess energy and stabilize newly formed nuclei during these reactions. As stars age, they produce elements up to iron, and during violent events like supernova explosions, massive floods of neutrons allow the creation of even heavier elements. Gold, platinum, uranium, and many other heavy elements are born through rapid neutron interactions. Every atom of these elements on Earth is evidence that neutrons once dominated extreme cosmic environments. Planets themselves owe their existence to neutrons. The materials that form rocky worlds, metallic cores, and atmospheres are built from neutron-stabilized atoms. Earth's layered structure, its magnetic field generated by an iron core, and its ability to support life all trace back to elements that could only exist because neutrons made their nuclei stable. Without neutrons, planets would not form, gravity would have nothing substantial to shape, and space would remain filled with little more than hydrogen gas. Life, in every form, is another direct consequence of neutrons. Biological molecules are composed of complex atoms arranged in precise ways. DNA, proteins, water, and organic compounds all depend on elements heavier than hydrogen. The stability of these elements ensures reliable chemical bonds and predictable reactions. Neutrons make this stability possible by maintaining balanced nuclei over immense periods of time. Life requires consistency at the atomic level, and neutrons provide that consistency by preventing atomic decay and structural collapse. Even time itself, as measured through radioactive processes, is influenced by neutrons. Many dating techniques used to understand the age of Earth and the universe rely on radioactive decay, which is often driven by unstable neutron configurations. These processes allow scientists to trace cosmic history, study evolution, and understand planetary formation. In this way, neutrons help preserve not only matter, but also knowledge about the universe's past. What makes this keynote especially profound is that neutrons achieve all of this without charge, visibility, or direct interaction with electrons. Protons define what an element is, and electrons determine how elements interact chemically, but neutrons ensure that these interactions can happen at all. They are the quiet enablers of existence. Their role reminds us that the most essential components of reality are not always the most obvious or dramatic. In conclusion, the idea that without neutrons, the structure of matter and the universe would not exist is not an exaggeration, but a fundamental truth. Neutrons allow atoms to form, elements to grow, stars to shine, planets to assemble, and life to emerge. They transform a simple universe into a complex, evolving one. By holding matter together at its deepest level, neutrons make everything else possible, proving that the unseen forces of balance and stability are the true rulers of the cosmos.